In this videotape, we're going to discuss integration by parts. Now, many of our integration formulas come from reversing differentiation formulas. If we take our formula for the product rule, assume we have u and v, and they're differentiable functions of x. We're familiar with the product rule. Derivative of a product of two differentiable functions of x would be the first function times derivative of the second with respect to x plus the second function times derivative of the first with respect to x. The derivative of a product is the first times derivative of the second plus the second times the derivative of the first. If I were to solve this for u dv dx, let's write this down here, u dv dx is equal to the derivative with respect to x of u times v minus v du dx. Okay, u dv dx, derivative of uv minus v du dx. If I take this basic formula from differential calculus, if I now integrate all parts with respect to x, let me indicate that here. Going to integrate both sides of this equation with respect to x. So integral with respect to x, integrate with respect to x. Just move this minus sign over here. We have this here. And now integrate with respect to x. We will wind up here with the integral of u dv equal to the integral of the derivative of uv. That's just going to be uv with a constant that we won't worry about right now because we'll pick that up over here, minus the integral of v du. The integral of u dv is uv minus the integral of v du. Okay, so we started with the product rule. We brought this over to that side. We had the integral of u dv dx was derivative of uv minus the integral of v du dx minus v du dx, and then we integrated both sides, and we wound up with this formula. This is the formula for common formula for integration by parts. Now, the idea with integration by parts is that the problem that you're trying to integrate, integral of say u dv, might be very difficult to integrate, but it's possible that if you've done it correctly, the integral of v du might turn out to be something much simpler to integrate. So you can go from something complicated to something that is easier to handle. Now, when would you use integration by parts? It's usually very good for integrating transcendental functions. For example, if you wanted to integrate ln x dx or inverse tan x dx, you wouldn't use it to integrate something that's already in basic form like sine x or cos x, but for log, exponential, trig functions that are not in basic form, it can be useful. It's good for integrating products of transcendental functions. For example, the integral of e to the x cos x dx. There's an exponential times a trig, products of transcendental functions, or products of algebraic and transcendental functions. For example, here, if you wanted to integrate x squared e to the x dx. So it's good for integrating, has other uses, but certainly good for integrating transcendental functions that are not in basic form, ln x, inverse tan x, etc. Products of transcendental functions. e to the x cos x. Or products of algebraic and transcendental functions. For example, x squared e to the x dx. This part being algebraic, that part being exponential, which is a transcendental function. Okay, so let's get started. Now, it's important to know that it's good for this, assuming that they're not in basic form. For example, if I wanted to integrate x e to the x squared, even though this is a product of algebraic and transcendental, you're supposed to know that this is in basic form. In other words, this is the integral of e to the x squared, x dx. If you let u be x squared, then du dx would be 2x, du would be 2x dx. If I rewrite this so that it comes out to be, it was e to the x squared, x dx. If I multiply by 2 and divide by 2 on the outside, the pink 2's here would cancel, back to where I started, but if I leave it like this, it's 1/2 the integral of e to the u, and 2x dx is du. This, of course, is one of our basic formulas, and the integral of e to the u du is e to the u plus a constant, and going back to x, it's 1/2 e to the x squared plus c. Okay, so this was in basic form. And therefore, you would not, even though it's a product of algebraic and transcendental, it's expected that you know how to do this, that this is in a basic form. Okay, let's say we wanted to integrate instead x e to the x dx. Now here we have a product of algebraic and transcendental. However, this is not in basic form. Okay, it's not an e to the u du, because if u is x, du would be dx. There's no way to account for this. So what we're going to do is to try to do this by integration by parts. Now, to do it by integration by parts, reminding you the formula is the integral of u dv is uv minus the integral of v du. We're going to have to break up the original problem into a u part and a dv part. The dv part will always include dx, and the idea is that the dv should be the most complicated thing that you know how to integrate, that is in basic form, and it always includes the dx. And in a choice, we generally choose transcendental, a trig, exponential, and so on, as more complicated than an algebraic function. So let's say we're going to let dv equal e to the x dx. Then u would be x. So we're going to try to consider this to be the integral of u dv, where u is x, dv is e to the x dx. Now, we're going to use this to figure out what v is and what du is. What we need v and du for this part of the formula. So from dv, we will integrate to get v. From u, we will differentiate to get du. Okay, remember, dv was chosen to be the most complicated thing that you knew how to integrate. Okay, so if I integrate both sides, I should have v equal to e to the x plus a constant, which we can ignore till the end. And similarly, du dx would be equal to 1, and du would be 1 dx. So we integrate the dv to get v, we differentiate the u to get du. Now, let's see what happens. This is now the integral of u dv. Accordingly, it should be equal to uv, which would be x e to the x minus the integral of v du. So it's uv minus the integral of v du. Well, the integral of v du is the integral of e to the x dx, and we have x e to the x minus, of course, the integral of e to the x dx is e to the x plus a constant. So we have our answer. We have that the integral of x e to the x dx, we now know it to be x e to the x minus e to the x plus c. And we can check. How does one check an answer? We simply differentiate the right-hand side and see if we actually get x e to the x. So the derivative of x e to the x minus e to the x plus c would be, well, here we have a product. It's x times the derivative of e to the x, respect to x, which is e to the x, plus e to the x times the derivative of x, which is 1, minus derivative of e to the x, plus the derivative of the constant, which is 0, and the plus e to the x and the minus e to the x cancel out, and we get x e to the x, which is what I want to show. That the derivative of the right-hand side is, in fact, x e to the x. So we have integrated or anti-differentiated x e to the x. We have found something whose derivative is x e to the x using this formula. Now, remember, the idea is that dv should be the most complicated thing that you know how to integrate, and u, hopefully, is something which is going to be simplified upon differentiation. Okay, let's start with now x cosine of x squared dx. Once again, we see a product of algebraic and transcendental, but it's up to you to know that this is in basic form. In other words, one of the basic formulas that you're supposed to know. In other words, we rewrite it as cosine of x squared times x dx. If we let u equal x squared, du dx is 2x, du is 2x dx. If you put a 2 in here, multiply by 2 here, and divide by 2 on the outside, this of course becomes 1/2 the integral of cos u du, which becomes 1/2. This is what I mean by one of the basic forms. Everyone knows the integral of cos u du is sine u plus a constant. So 1/2 sine of x squared plus a constant. Okay, but while this is in basic form, this needs integration by parts. And we have x cos x dx. Similar to the problem that we just did. Okay, x cos x squared was basic, but x cos x needs integration by parts. Once again, we're going to try to rewrite this as u dv. The integral of u dv is uv minus the integral of v du. dv should be the most complicated thing that we know how to integrate. So I'm going to let u be the x and the dv be the cos x dx. So u is x, dv is cos x dx. And I'm going to differentiate to get du and integrate to get v. du dx is 1, du is 1 dx. Integrating both sides here. V is sine x plus a constant, but we're just going to use the sine x. The constant we'll take care of later. So, according to our formula, we're going to write uv x sine x minus the integral of v du. So minus the integral of sine x dx to give us x sine x minus, now the integral of sine is minus cos x plus c, for an answer of x sine x plus cos x plus c. Okay, and this of course can be checked by differentiation. The product rule, the derivative would be x times the derivative of sine x, which is cos x, plus sine x times the derivative of x, which is 1, and then the derivative of cosine is minus sine x, so you wind up with just the x cos x. Now, what if you make a mistake in picking your u and dv? Whereas in our problem originally was x cos x dx. Suppose you decided, I want to let u be cos x and dv be x dx. Okay, it can be broken up this way. still be the integral of u dv. Now, if we do that, if we let u be cos x and dv be x dx, we can still differentiate to get du. We can still integrate to get v. Let's see what happens. The derivative of cosine x with respect to x is minus sine x, so du would be minus sine x dx. And here, integrating both sides, v would be the integral of x dx, which would be x squared over 2 plus a constant which we will temporarily ignore. Now what happens here? We're going to get u v minus the integral of v du. u v would be x squared over 2 cos x minus the integral of v du. Well, v is x squared over 2, and du would be minus sine x dx. So in other words, this is coming to x squared over 2 cos x minus a minus plus. You could take out the 1/2 the integral of x squared sine x dx. X squared over 2 cos x plus 1/2 the integral of x squared sine x dx. Now, if you look at the original problem involving x and a trig function, which we said was hard to integrate, we couldn't do it to begin with, we've now wound up doing it this way with something which is worse. This is worse than what we started with. Okay, so that's a step in the wrong direction. We now have x squared times a trig function, whereas before we had just x times a trig function. If you see that happening, that means you've made the wrong substitution. Okay, so you haven't made a mistake. You've just, remember, any kind of integration is a certain amount of guesswork is involved. Okay, you haven't made a mistake. You've guessed wrong. The same way when you started long division, which was an inverse operation, you said, geez, does this thing go in 6 times? And you see, nope, it's too much. I'll try 5 times. It's a certain amount of guesswork in any inverse operation. And integration is an inverse operation. So you have a certain amount of guesswork. If you guess right, fine. If you see it's getting worse, scrap it and try to guess something else. In this case, our original guess was the correct one. And generally, if you let dv be the most complicated thing you can integrate, I mean, it takes a little experience to figure out what's the most complicated thing, but generally you'll do all right. Okay, so if you see it getting worse, okay, you're going to scrap it and try something else. For our next example, let's try integrating inverse tan x dx. Well, here there's not really a lot of choice. We do not know how to integrate this, so this can't be part of dv. So in this case, dv is simply going to be dx, and u is going to be inverse tan x. You do not have the option of making x dx dv. This is part of the inverse tan. Okay? dv is the most complicated thing I know how to integrate. The only choices are dv is dx or the whole thing. Obviously, if I could integrate the whole thing, I wouldn't be doing integration by parts. So really no choice in this matter. U is inverse tan x, dv is dx. Now, to integrate both sides, we get that v is equal to x plus a constant, and to differentiate, du dx would be the derivative of inverse tan x, which is 1 over 1 plus x squared, and du would be 1 over 1 plus x squared dx. Okay, now, using our formula, the integral of u dv is going to be uv minus the integral of v du. uv would be inverse tan x times x, or x inverse tan x minus the integral of v, which is x, times du, which is 1 over 1 plus x squared dx. So v du, x times 1 over 1 plus x squared dx. And once again, we have a situation where the integral on the right here is easier to handle than what we were faced with originally. Okay, so what do we have? X inverse tan x minus, now, this is almost in the form du over u. or I guess dw over w, because I've already used up my u. But if w is 1 plus x squared, then dw would be 2x dx. So if you were to multiply by 2 and divide by 2 on the outside, this becomes 1/2 the integral of dw over w, or 1/2 the integral of dw over w, which is ln of the absolute value of the denominator, ln the absolute value of 1 plus x squared plus c. Of course, I don't need the absolute value because 1 plus x squared couldn't be negative anyhow. So x inverse tan x minus 1/2 ln of 1 plus x squared plus c. Okay, for my next example, let's try x ln x dx. Now, I know in general I say dv should be the most complicated thing I can integrate, and we've been taking the transcendental part. In this case, we don't have that option because I can't let dv be ln x dx because that's not one of my basic forms. I don't know how to integrate ln x dx. So I'm going to have to rewrite this as ln x times x dx, and I'm going to let dv be the x dx and ln x be the u. Okay, u is going to be ln x, dv is going to be x dx, and I'm now going to go over to figure out what du and v are. Well, to integrate both sides here, the integral of dv, v, is going to be the integral of x, which is x squared over 2 plus a constant which we're temporarily postponing till the end of the problem. And du dx, derivative of ln x, with respect to x is 1 over x, so du is 1 over x dx. So we have the integral of u dv is supposed to be uv minus the integral of v du. So what do we get? uv. That's x squared over 2 ln x. Ln x times x squared over 2 uv minus the integral of v du. v is x squared over 2, and du was 1 over x dx. Okay, that's not terrible. We have the x squared over 2 ln x minus, now, this 2 I can take out in front, minus 1/2 the integral of x squared over x is just reduces to x, so the integral of x dx, which gives me x squared over 2 ln x minus 1/2. Now the integral of x, or x to the first power, of course, is x squared over 2 plus a constant. So my final answer, x squared over 2 ln x minus x squared over 4 plus c. And of course, this can be checked by differentiation. Now, sometimes you have to use integration by parts more than once to solve a problem. For example, let's say we're doing x squared e to the x. That has to be integrated. We start off normal way. We can let dv be e to the x dx, u be the x squared. Notice this is different from x e to the x squared, which I started this videotape with. This is in basic form. Okay, they both involve x squareds and e's, and so, but this is e to the u, almost du. We did this, the first problem we did on the tape, putting a 2 in the 1/2. This is a lot different from this. Okay, now, going to let u be x squared and dv be e to the x dx. And as always, we're going to differentiate u, and we're going to integrate to get v. Derivative of u with respect to x is 2x, du is 2x dx. And the integral of e to the x dx, of course, is e to the x plus a constant. Now, this is going to be equal to uv minus the integral of v du. uv is x squared e to the x minus the integral of v du. It's uv minus the integral of v du. If I multiply v times du, I would get e to the x 2x dx. Okay. Now, this is x squared e to the x. I can take out the 2, minus 2 the integral of x e to the x dx. Now let's look at what we're faced with integrating here. We have to integrate x e to the x dx. It's not worse than what we started with. We're certainly making progress. Do you remember we had that one where after one integration we were worse off than we started? We're not worse off here. Here we had x squared times e to the x. We brought down the power, and now we have x e to the x to integrate. Okay, we feel that if we do it again, maybe it'll work itself out. Certainly it's worth a chance. It's not like it's gotten worse. It has improved. So let's try it. We're going to repeat the integration by parts over here. We're going to break this up. We're going to now we're going to have a new dv and a new u. Oh, we can indicate that like this, with a little tilde over the u and the v, little squiggle there. dv, the new dv, is going to be the most complicated thing we can integrate. The new u is what's left over here. So we have the new u is x, the new dv is actually the same as the old dv. It's a good habit to just change your letters around here. Now the new du is going to be dx, and integrating both sides, the new v is going to be e to the x plus a constant. So the integral of the new u dv, okay, this we have still the x squared e to the x minus 2. Now what's going to go in here, the x squared e to the x minus 2. Now this new thing here is going to be the new u times the new v minus the integral of the new v times the new du. The new u, new v, minus the integral of the new v, new du. So the new u, new v is x e to the x minus the integral of the new v du. The new v du is just e to the x dx to be integrated. Okay, so now we're in good shape, because what do we have? We have x squared e to the x, now minus 2 x e to the x minus 2 times minus, so plus 2 times the integral of e to the x dx. Okay, remember we pulled out this minus 2 to make it a little simpler in here. We now have to distribute the minus 2 back through the parentheses, through the brackets. So it's minus 2 x e to the x minus 2 times minus this, so it's plus 2 times the integral of e to the x dx. And now we can simply finish this problem up. X squared e to the x minus 2x e to the x plus 2. Now finally, the integral of e to the x dx is e to the x plus c. So that gets us to the end of this problem, which of course can be checked by differentiating the answer to make sure that you get x squared e to the x. So the answer is x squared e to the x minus 2x e to the x plus 2 e to the x plus c. Now, I wanted to mention something to you. When you have to do two integrations by parts, okay, over here we saw that we did it once, and we see that we're improving, but we're not finished. Don't change the flavor of the integration. Okay, for example, if over here I had now let u be, the new u be e to the x and the new dv be 2x dx, which could certainly be something you think about doing because it's sitting right here, you would wind up undoing what you just did, and you wind up with an identity. So if you're going to do more than one integration by parts because you see it's improving, if your original one had dv equal to e to the x dx, your next one should also have dv equal to the e to the x dx. Don't switch it around and let u be now the transcendental part and the dv be the algebraic part, because it's going to serve to undo everything you just did, and what you wind up with when the smoke clears is just an identity. Okay, so if you're letting dv be the transcendental part and it's working, keep with it. Okay, for our next example, let's try the integral of e to the x cos x dx, a product of two transcendental functions. Okay, I'm going to let dv be that and u be that. See what happens. Okay, so we want to integrate e to the x cos x dx, and we're just going to let dv be cos x dx and u be e to the x. Turns out it really won't matter. You could also do it by letting u be the cos x and the dv being e to the x dx. This case, you might say, well, how does she know that this is a more difficult thing to integrate? It's really not. And it turns out the problem can be successfully completed either way. But it's written this way, so I'll let dv be cos x dx and u be e to the x. Now, to differentiate, du is e to the x dx, and integrating both sides, v is sine x plus a constant. Okay, so this is going to be the integral of uv minus the integral of v du. uv, which is e to the x sine x minus the integral of v du. v du sine x e to the x dx. Now, let's look what we're dealing with. Originally, we were dealing with integral of e to the x cos x dx. Now we have to integrate e to the x sine x dx. I wouldn't say it's any worse than what I've started with. It's not any better. It's more like a lateral move. Okay? Now, when it's worse, you certainly should stop what you're doing and rethink your substitution. If it's better, you keep going. When you have more like a lateral move where it's no worse, no better, give it another shot. See what happens. Sometimes very interesting thing shows up, and that's what's going to happen here. Okay, the only thing is, when you're doing more than one integration by parts, and I mentioned this before, it should have the same flavor as the original one. If something is working, you want to stay doing what you've been doing. So if originally u was the e to the x and dv was the trig part, I want to do that here as well. So I'm going to rewrite this as e to the x sine x minus the integral of e to the x sine x dx. So that when I make the new substitution, the new dv is going to be sine x dx. The new u is going to be like the old u, e to the x. Okay? So if the new u is e to the x and the new dv is sine x dx, the new du is e to the x dx, and integrating the new v, the integral of sine x dx is minus cos x plus a constant, which we're temporarily ignoring. Okay, so let's see what we have so far. The original problem, we rewrite it over here so we can see what we're dealing with. The original problem was the integral of e to the x cos x dx, which we rewrote as e to the x, which we wrote by integration by parts e to the x sine x minus the integral of e to the x sine x dx. And now we're going to put in here the new u times the new v minus the integral of the new v du. Now, the new u, the new v, gives us e to the x times minus cos x, or minus e to the x cos x minus the integral of the new v du. Minus the integral of the new v du, which is minus e to the x cos x dx. Okay, let's see what this is. Integral of e to the x cos x dx. We have e to the x sine x minus a minus, so plus e to the x cos x, minus a minus, minus 3 minuses, so negative integral of e to the x cos x dx. Okay, so the integral of e to the x cos x dx, e to the x sine x, minus a minus plus e to the x cos x, minus, 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 so minus the integral of this. Now, is this better or worse than the one we started with? It's not better, it's not worse, it's exactly what we started off with, and it's interesting. The integral that we originally wanted to handle has now appeared on the right side, but with a minus sign. This is good, okay? When this happens, what you do is you say, I have this thing, I don't know what it is. It's this plus this minus the same thing. Add this to the other side. So this is thing I don't know what to do with, and I have it again over here, so I'm going to have two of these integrals. So I had this integral, and it appeared over here also with a minus sign. I add this integral to both sides. It drops out here. I have this integral and this integral again, so I got two of these integrals. Okay, 2 times the integral that I'm trying to find equals e to the x sine x plus e to the x cos x. So what I'm going to do is divide both sides by 2. If I divide by 2, I'm going to get what I'm looking for, which is the integral of e to the x cos x dx equals e to the x sine x plus e to the x cos x all over 2 plus, now it's the end of the problem, so I'm going to write a plus a constant at the end. Let's look at that again. We had this integral. Here it was on the other side, but with a minus sign. Okay, we did one integration by parts, and we wound up with something involving e to the x sine x. We did it again, we went back to the e to the x cos x, but with a minus sign here. If we add this to both sides, drops out here, comes over here. We have this integral and this integral again, so we have 2 of these integrals equal to that. So if you want to know what this integral is equal to, simply divide by 2. It's 1/2 e to the x sine x plus e to the x cos x, and then since it's the end of the problem, that c that we had been leaving off till the very end, we'll just tack on the plus c. Okay, for our last example, let's try the integral of secant cubed x dx. Okay, now if we want to integrate secant cubed x dx, the first instinct is, what's going to be d? It's not in basic form. What should be dv? What should be u? You might think, well, you have no choice. dv should be dx, and u would be secant cubed x. But actually, you do have a choice. The most complicated thing that I know how to integrate is really secant squared x. If I rewrite this as secant x times secant squared x dx, and if I let dv be secant squared x dx, that's really the most complicated thing that I know how to integrate. So I'm going to let u be secant x, dv be secant squared x dx. And I'm going to differentiate u, derivative of u, derivative of secant x with respect to x. Derivative of secant x is secant x tangent x. Derivative du would be secant x tangent x dx. And we're going to integrate to get v. The integral of secant squared x dx is, of course, tangent x plus a constant. Okay. So let's see what happens here. We have uv minus the integral of v du. uv would be secant x tangent x minus the integral of v du. Well, v is tan x, and du is secant x tan x dx. Okay, let's see what we have so far. The original problem, if you remember, was the integral of secant cubed x dx, which I broke into secant times secant squared. And we've done this, and we have now equal to secant x tangent x minus the integral of, we have secant x tan squared x dx. Okay. Now, how do I integrate this? I'm going to use something of a trigonometric trick here, okay, which you might not like, but I have to show it to you. We know that sine squared x plus cos squared x is 1. This is a common trig identity. If we divide through by cos squared x, we will get another trigonometric identity. Tan squared x plus 1 is 1 over cos squared x, which is secant squared x. Or tan squared x is secant squared x minus 1, which is what I want to employ in here. Why I'm doing this? Well, this comes with experience, but it's going to help. Okay, so for tan squared, I'm going to replace it by secant squared x minus 1. So let's see what happens. I'm not doing integration by parts again. I'm just rewriting the integral of secant cubed x dx. It's equal to secant x, excuse me, it's equal to secant x tangent x minus the integral of secant x, and for tangent x, I'm going to replace it by secant squared x minus 1. So what do I have? The integral of secant cubed x dx is secant x tangent x minus, now let's distribute the secant through the parentheses, minus secant x dx. So minus now secant times secant squared minus 1, secant cubed x minus secant x dx. Okay, so let's see what I have. I have the integral of secant cubed x dx is secant x tangent x. Now, let's break this up to two integrals. Minus the integral of secant cubed x dx minus a minus plus the integral of secant x dx. Now, here we have the same integral that we had over here, but with a minus sign. If we add this to both sides, it drops out here, comes up over here, we wind up with 2, again, 2 times the integral that we're looking for, equal to secant x tangent x plus the integral of secant x dx. Okay, and now dividing by 2, the integral of secant cubed x dx would be secant x tangent x, divide that by 2, plus say 1/2 the integral of secant x dx. So we added this to both sides, plus the integral, it dropped here, plus the integral here, we get 2 of that integral. Equals this, secant x tangent x, plus the integral of secant x dx, which is one of our basic integrals, which we're supposed to know. Okay, so to finish this up, the integral of secant cubed x dx, secant x tangent x over 2, plus 1/2. Now, the integral of secant x is ln of the absolute value of secant x plus tan x, and then the end of the problem plus c. So here we have the answer to the problem. Once again, just like in the previous problem, we wind up with having the integral we're looking for on the other side of the equal sign with a minus sign, and if we bring it over to the left side, we'll get 2 times that integral. We divide by 2. And here we didn't need another integration by parts, we just needed to know the integral of secant. Of course, we had that trigonometric trick. Okay, that brings us to the end of this tape.